In this video, we'll develop the concept of domain for multivariable functions. The notion of domain is same as what you studied prior in calculus. Today, we would just extend this idea to multivariable functions. Before going into the details of concept of domain for multivariable functions, let's first recall the definition of domain and range what you have studied earlier in calculus. Well, a domain is the set of all real numbers for which function f is defined. Well, now the question is, what does it mean by f is defined? So, there are basically two conditions which provide us a defined function. So, first condition is output should be a real number. It means that output should not be in the form of square root minus 1, that is, there should not be a negative number inside the square root, which basically gives imaginary number. So output should not be a complex number, it should be a real number. Now the second condition is output should not be 1 by 0, which is basically infinity. So output should be constant defined number, it should not be infinity. Well, what is range? All possible outcomes for the values of domain of f is called range of f. Range basically are the outcomes, and it totally depends on the values of domain. So all the possible outcomes for the values of domain of f is called range of f. Well, let's recall about the graph of single valued function, and then we would extend this idea to the multivariable functions, to the graphs of multivariable functions. The graphs in single valued functions are two-dimensional. So here we have the x-axis and this is y-axis, and their intersection is origin. So we have a two-dimensional curve. Y is equal to f of x. Here x is independent variable and y is dependent variable. All the values of x are inputs and all the values of y are outputs. So you can see here all the values of x corresponds to the values of y. So if we take a random point on this curve, its coordinates are x1 and y1. It means this point has x coordinates, which is input x1, and the corresponding output is y1 on the x-axis. So x1 is input and its corresponding output is y1. So this curve is basically made up of infinite such points with two coordinates, x coordinates and y coordinates. Here x coordinates belongs to input values and y coordinates belongs to output values. So let's now explore the concept of domain graphically. So all the values on x-axis in which the function is extended is the domain of f. So all the values between these two values of x-axis are the values in the domain set. So similarly, all the values of y-axis in which the function is extended is the values of range. So all the points on y-axis between these 2 points is the range of f. So basically domain relates to the input values and range relates to the output value. So you might have observed that in 2 dimension the domain is 1 dimension. That is, domain is the set of real number and the real number line is 1 dimension. So let's suppose we have a multivariable function of 2 independent variable, which is basically the 3-dimensional surface. Its domain would be in 2 dimension. So this is the basic idea of domain for multivariable functions. Now let's extend this idea to the multivariable function of two independent variable, which is basically a three-dimensional space. So here we have this red line represents x-axis and this green line is y-axis and this blue line represents z-axis and their intersection is origin, and this plane with grid lines is the xy plane. So here we have a ball on the xy plane. Let's explore its coordinates. So here the distance of this ball from origin along x-axis is -2, that is 2 units in the negative side of the x, and the distance of this ball from origin along y-axis is 4 units. So its coordinates would be -2, 4 if we are discussing them in 2 dimension. If we are discussing them in 3 dimension, then there are 3 coordinates and the third coordinate would be 0, that is with no height. So basically z-axis represents the height of the object. So here the height of the object is 0 because it is on the floor, it is on the xy plane. So if I throw this ball upward with some height, let's suppose this height is 3 units, so now its coordinates would be -2, 4 and 3. So 3 units is basically its height. So if we have such infinite points on the xy plane and if we take them upward with some different heights, then it combines and make a surface. So this surface is basically made up of infinite such points which has 3 coordinates x, y and z, where we can say xy are the points on the xy plane, which we can say are the inputs, and its output is its height, which is represented by z. So it can be represented as z is equal to f of xy. Here xy are the points on the xy plane, which is basically the zero height of all the points on the surface. So if I extend the idea of domain in three-dimensional surfaces, the domain is basically the image of this surface on the xy plane. So all the points in this xy plane under this surface is the domain of this specific function f, and all the points on this shadow that is in the form of ordered pair is the domain of this function. So here you can see the major difference in the domain of single valued function and bivariate function is that in that case we have a domain in the form of single values in the form of real numbers, and here in three-dimensional surface the domain is in the form of xy plane whose points are in the form of ordered pairs. So there we have two independent variables, we have two inputs and the single output, and here the output is in the form of single real number. So this is basically the domain of three-dimensional surfaces. Well, now this example is just to make your minds very clear about the concept of domain for three-dimensional surfaces. So here we have the circular paraboloid, and if I imagine its image, its shadow right below on xy plane, then it would be a circle. So all the points on the boundary of this circle and all the points inside this circle is the domain of this particular function. So if I draw this graph on the xy plane, so here it is the domain of this function. Well, if I summarize the whole discussion, I would say the major difference between the domain of single valued function and the bivariate function is that in single valued function we have domain is the set of real numbers, and in the bivariate function, that is the function with two independent variables, the domain would be in the form of ordered pair. The domain would be a subset of the xy plane. So here we can say the domain of any function is always one dimension lesser from its surface. So if I have two-dimensional problem, its domain would be in one dimension. If I have three-dimensional surface, its domain would be in two dimension. If I have four-dimensional surface, its domain would be in three dimension, and so on. So now you are very clear with the concept of domain for single valued function and for multivariable functions.